All right, guys, we are getting there. The end is in sight. I'm going to tell you about how the electrons fill up an atom. So like the order they fill those different orbitals, and there's a couple rules behind that, and there's one more quantum number we got to get through, but we're getting there. We're getting there pretty close. So in this diagram, you see, this is the actual order that the electrons will use to fill up an atom. If you're going to put electrons in one at a time and like build up an atom, this is the order they always go in. You see something a little bit weird here, like the sublevels have all split up. Whenever you have a multi-electron atom, so multiple electrons in there, there's electron-electron repulsion, and that changes the energies of these orbitals. It causes them to kind of fan out, and there's a little bit of a crossing here. So I'm going to show you a little bit later on in this actual talk of how to use your periodic table to keep track of this, but the order is 1s, then 2s, then 2p, 3s, 3p, then it goes 4s, 3d, 4p, and so on. I'm going to show you how to use your periodic table to keep you straight on that, but that is the order, and you will have to memorize that. All right. And that's just in other stuff I had. So yeah, many electron atoms, the orbitals on the same energy level are no longer degenerate. Yes, they spread out. All right, let's get to the last quantum number. So back in the 1920s, they figured out that electrons, two electrons in the same orbital, they didn't have exactly the same energy. It's kind of like they had a higher resolution camera, and what looked like one little line was actually two lines. And they figured out, oh, so there's like two electrons there, and they're slightly different in energy. And the electrons were acting as if they had a magnetic field. So when charges move, it creates a magnetic field. So these electrons were acting like they were spinning and creating a magnetic field, which would either align perfectly with or perfectly against an external magnetic field. And this gives us our last quantum number. It's m sub s. All right, so it's the spin quantum number. And so we're talking about the electron spin. And there's only two values of it. So it's either plus a half or minus a half. So we say it's plus a half, and we write, God, I can't talk. We draw that as an arrow pointing up, so we call it spin up. And if it's pointing down, we say it's spin down, and the spin value is minus a half. So those are the only two values of m sub s. Now, the Pauli exclusion principle says that no two electrons in the same atom can have exactly the same energy. Another way to think of that is no two electrons in the same atom can have identical sets of quantum numbers. The order we always do the quantum numbers in, it's always n, l, m sub s. So n is the energy level, l is the shape, m sub l is the orientation, and then the last one is going to be, is it spin up or is it spin down? So I can have two electrons on the same energy level, in the same shape orbital, in the same orientation orbital, but one's going to be spin up, one's going to be spin down. So that's why there's two electrons per cloud. So one will be spin up, one will be spin down. There's something called an orbital diagram. We use boxes to represent the different orbitals. All right, so if I'm going to do an orbital diagram for lithium, it's going to show me where all of the electrons in lithium are. So I look at the periodic table, I find lithium, I see its atomic number is 3. That means it has 3 electrons. Where do those 3 electrons go? Well, the first orbital that fills up is 1s. So I put one of these little half arrows in, and I start with it pointing up. So we always go in, spin up first. So the half arrow pointing up, that's 1 electron. The next electron, well, it's like, oh, where am I going to go with that? Way up here or in the same box? It's going to go in the same box, right? It's lower in energy, but it's going to go spin down. Now this is filled, so the 1s orbital can only hold 2 electrons. So that third electron has to go up to the 2s. So you put that one in as spin up. Cool. All right, that's that. Now, what happens when we get a little higher up, when we get to like the p subset or the d's, where there's degenerate orbitals? So these are called degenerate because they're all the same exact energy. Remember, there's px, py, pz, the 3 different p orbitals that are like peanut shaped. They're just pointing different directions. All right, let's say I'm doing oxygen. I'm going to use oxygen. So oxygen, I have, how many electrons would oxygen have? Should have 8. So where are those 8 electrons going to go? Gosh, can't talk today. Well, the first 2 are going to go in the 1s. The second 2 are going to go in the 2s. Then when you get up here to the 2p's, they're going to go in one at a time. So spin up, spin up, spin up. And then you come back, dink, and then you start pairing them up. So they always go in one at a time. Whenever you hit a degenerate set, they go in one at a time until everything's filled. Then you start pairing them up. That is called HUND'S rule. So it says for degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin as maximum. That's just kind of a confusing statement, but that is the textbook version of it. And what we just did there is called the Aufbau principle. So that just means building up. So when we build up an atom, we always start with the lowest energy orbitals available. We fill it, and then we move to the next lowest. And then once we get to these sets like this, we go one at a time. So spin up, spin up, spin up. Then you would go spin down. The next one will go here, spin down. The next one will go here, spin down. And then after 2p, you got 3s, all right? And then you keep going. So we're going to keep filling these orbitals in order of increasing energy. All right, so the different blocks, there's what we call blocks in the periodic table. And I have a really big version of this on the next slide. And they actually correspond to the different types of orbitals. So let's look at that. All right, so here's your periodic table. This is called the S block. So these first two columns over here are the S blocks. And even helium over here actually counts as S block. All right, so that's S block. And then over here, this is what we call the P block. Here's the D block. And then down here, kind of separated from the table, that's the F block. The F block actually would be sticking out kind of in here, and the actual periodic table would look really long and weird. So they just kind of pull it out and then mash this back together. So that's not hanging out here. But these are your different blocks. So when you fill, right, the first row here, that's 1. Second is 2, 3, right? Easy. The only thing to keep your brain around is like, okay, the D, once you get to these D orbitals, they are offset. So notice you go from 4s to 3d back to 4p. So the S block and the P block are always matched up. Like whatever row you're in, that's fine. That's cool. 6 and 6, 7 and 7. The D blocks are sunk by 1. All right. So it goes 4s, 3d, 4p, 5s, 4d, 5p. Now it gets crazy. Once it gets to 6s, things get crazy because there's another crossing. So it goes from 6s, boom, jumps down here to 4f, comes back up here, 5d, 6p. And then after 6p, you go 7s, 5f, 6d, 7p. So it's a little crazy down there. Most of the stuff we're going to do, I'm going to keep it on the upper side of the table. But this will help you remember how they fill. So if I look at this, like 1s, 2s, 2p, 3s, 3p, 4s, 3d. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, right? It's the same thing. All right, so this is connected to the table. All right, so when we're putting these things in there, that is the order. You're going to have to get used to that order. I would say use the table. Get used to the table. Color your table in. Get some colored pencils. Get something. Scribble it around. But this will help you a whole lot when we start doing electron configurations, which I'll show you in the next video. All right, see you then. That'll be the last one of this chapter. Woo!